Alrighty, good afternoon everyone, and welcome to UQCS in week 12 already. Hello, Anton. Today we have Luna on a talk of parser combinators and parsers in general, so please welcome Luna.
Hello everyone. I've just found out that when you put a slideshow in full screen, it covers both of your screens, so I don't get to look at my script while I'm doing this. So this is going to be great. So today I'm going to be doing a talk. It's called Parser Combinators in N different languages, and we will find that N is only going to be 3 because that's all the time that we have left. But the whole point of the talk is going to be that Parser Combinators are just sort of a technique of writing parsers for string formats that you can kind of do in your own favorite language, whatever you want. My username is Viluna. You might have seen me on Discord and whatever. One of the languages we're going to be doing is Rust, because I really like Rust. That's the intro. So welcome. About me, I go by many names. Luna Barella. I'm a maths and computer science student here. I'm in my 5th year, and you may know me if you took Comp 3400 last semester because I was one of the tutors. And I wrote these slides last night, so I don't know. I was kind of going insane when I was doing this. So first of all, why are we talking about parsers? So when I was a kid, I started programming, and I had to write a few manual parsers. For example, I wanted to write my own programming language, but I didn't know how to write a parser, and I tried to do it in Python. It didn't go well. I concluded that writing parsers sucks, and I really hated it. And I felt this when I was doing, for example, CSD 2002. We had to write a parser for a format, and that was like the thing that I did the absolute worst at. And then later, I took Comp 3400 and Comp 4403, which are 2 courses that cover stuff that's kind of adjacent to what we're going to be talking about today. And I concluded that parsers are pretty sick. They're actually pretty cool if you know how to do it. Here's an artist's impression of that moment. I started later writing one of my own projects, which was a video game. And to parse this sort of the format for the levels, I had to write my own parser. And I was writing this in Rust, and I used a combinator library called nom, which we're going to be having a look at later. And I concluded that parser combinators are really fun, and that you can do them in anything, not just Haskell, which is where I learned it. Haskell's functional programming language. We're not going to actually be talking about Haskell today, but we're going to be talking about some things coming from such languages. So, as I said, N programming languages. The point of this talk is to basically say that you can learn this stuff, you can go home and just do it in whatever you like, and it's just really fun. It's a technique, not a library, necessarily. But we will only look at 3 languages today. The first one is JavaScript. I'm sorry, but I chose it because it's really simple and it's friendly, and it has all of the things that we would want out of, something that we can implement combinators in. And then I also like Rust, so I wanted to do it in Rust. And finally, I also chose C because I thought it would be really funny. It's not a good language to do it in. I didn't even want to get a logo without the transparency. This is just what I downloaded, and I just figured it fit really well. All of the code for this is on a GitHub that I have not made public because I forgot to do it. But if you want to go to that URL, then I'll make it public eventually, and all of the code plus more is there if you want to go and have a look at it. So, first of all, what are we parsing anyway? This is sort of a question, because when we go to write a manual parser using just string functions, it's common to just get stuck right into it and be like, I want to turn my string into some kind of data, I'm just going to hack at it. But if we want to write a parser for real, we first want to think about what the format is that we're parsing. We want to define it. And the way that we do that is by writing something called a grammar. And this is covered more in Comp 4403, compilers and interpreters. I don't have the time to do this justice, so from now on, we're talking about something called a context-free grammar. Anytime that I say grammar, just find and replace and pretend I said context-free grammar. Context-free grammars are really great because they give us the ability to sort of algorithmically turn a grammar into a parser in a bunch of different ways. So let's have a look at a grammar, just to sort of get used to it. We normally present these in a format which is called EBNF, or extended Backus-Naur form. Well, there's a bunch of different ways to do it, but this is how we did it in compilers and interpreters. And so EBNF is made up of a bunch of rules defining the structure of a text and giving that structure a name. So we have, for example, a symbol name, and then we write this little funky equals sign, and then we write whatever the text is made of right to left. So here's a grammar. Name equals UQCS. This parses a string format. It has exactly one string, and that's UQCS. And that's not very interesting. So, I mean, UQCS is interesting, but the grammar is not interesting. So here's another one. Grammars can have alternatives. So they could just be, for example, one thing, or they could be multiple things. And we represent this using this pipe operator. So what this means is that greeting is one of these strings. We have hello, good day, and hi, and greeting could be one of these three. So that's kind of, grammars are sort of writing these out in a declarative way, in a kind of a similar way to that we think about text formats. We say things like a greeting is this, or so on and so forth. And this will become more apparent later on. So here's another grammar. A message is a greeting followed by a comma and a space followed by a name. That kind of thing, right? So in this sense, we're chaining, we can sort of allow for multiple alternatives. We can also chain multiple substructures together, and they read left to right. So what this grammar defines is these strings. Basically, a message is just a greeting. A greeting could be one of our three greetings here. And then a comma and a space, and then a name. There's only one name, UQCS, that is the only acceptable name. And nothing else is acceptable. So yeah, we effectively have defined a text format that specifically, you know, it sort of defines the structure, and by defining what this text format is, it also defines what it isn't. So let's look at some more grammar rules. Anything that's written in square brackets is optional. So you could have that, or you could not. So this grammar matches nothing, or just UQCS. If it's in curly brackets, it could be 0 or any number of repetitions of that grammar. So 0, empty string, or UQCS, or UQCS, UQCS, or so on, you know, towards infinity, theoretically. So here's an example grammar, and let's sort of examine it a little bit. This matches integers, and I'm being a bit strict here in that you can't start an integer with the digit 0 unless it is 0. So in this case, we've defined a symbol which is going to be 1 to 9, and it's just all of the digits from 1 to 9. We've done a similar thing with the digit here. This is just all the digits from 0 to 9. And then we've said that an integer is either just 0, or it is a single digit from 1 to 9, followed by any number of digits from 0 to 9. And that gives us a grammar for matching integers. And so, you know, yeah, as I've said, this is how you read the grammar. We will get to parsers in a moment, but this is very important because this gives us a way of just turning this into a parser that will allow us to parse whatever we need. Here's another one, a list of integers. So I'm reusing my integer parser here. And this is just a grammar that defines a list. And we'll take a little bit of a moment here. An element is just an integer. We'll see why I did that in a moment. And a list is just an open bracket around an inner list around a closed bracket. An inner list, in turn, is optional, so it could be empty. You can have an empty list. Or it's going to be one element followed by any number of commas and then elements. So if you think about it, it can be like element, or element, comma element, or element, comma element, comma element, and so on and so forth. And this just gives us something. You can't put commas at the end, which some people like doing that, and I like doing that, but this is just simple for now. Now, quick question. how would you take this grammar and turn it into a recursive list? So instead of just matching elements as just integers, so we could just have 1, 2, 3, 4, 5, or whatever, you could also, the elements could also be lists, and we can nest them sort of infinitely. Maybe a naive way would just be to add it to the end of element, right? Like, we just do that. And yeah, we can do that. In fact, this is the grammar which defines a recursive list. And so what I think is great about grammars is that they are just, like, they might seem a little bit weird, like, why are we breaking this down? Is because they're extremely extensible, and you can define complicated formats in a way that is like, almost just like human speech, right? Like an element is either an integer or another list, right? And it just, we've barely made any change, and we've created something more complicated. So as you can see, it matches nested lists. So we have the ability to, sort of now nest them, and it will only match it if the brackets are matched. So we just get bracket matching for free from that. And of course, as I said, we can turn this straight into a parser which matches our nested lists, which would be a pretty hard thing to do if you were doing a manual parser. You would need to create a stack to make sure you ensure that all of the brackets are open and closed. With this, you can literally generate a parser from this graph. You don't even need to do any work, but we are going to do work because I think work is fun. So how do we do it? Part 2. What is a parser anyway? Well, there are many different ways of writing parsers, and this whole time I've been using the word parser and not really kind of saying what it is. So in the abstract, a parser it's a function that takes a string and turns it into something else, and it can fail, or it could fail. And the way that we're going to be doing that is by treating parsers as functions. And so this way is called recursive descent. Parser combinators, which we will get to, is kind of a subset of recursive descent. It's backtracking recursive descent. Once again, we are taking like a tiny peek into the world of parsers. We're not going to be able to cover everything. But we're going to be using something called recursive descent. And this technique is where we take our grammar and we directly translate it into just functions. We write a function for every one of our production rules, and I know this pseudocode is kind of simplified, that we'll get to how it actually works later. But the idea is that we just take our grammar rules, which are called productions, by the way, I think I might have forgotten to say that, and we turn them into functions to parse that particular structure. And from that, we can sort of define functions for small productions and build them up bigger and bigger and bigger until we get something more complicated. Okay, so how do we do that? In this technique, we need to define what a parser function looks like. So as I said, parser functions take strings and they turn them into stuff. But in this case, because we want to chain them together, we're going to do something a little bit strange. Parser combinators functions, or parser functions, take in a string and parses as much of the string as it can, and then returns what it parsed, as well as whatever it didn't parse. And this just means that we can run one function, figure out what it parsed, and then run another parser function on whatever it didn't consume, and through that way we can chain functions together, which we will eventually come to see. They can also fail. If you give them a string format that doesn't match, we have to be able to error. So here's an example. Here's a function. It's called parseInt. It's a black box. Well, actually, it's magenta. Say hi, parseInt. Now, if we give parseInt, we just are going to pretend parseInt parses an integer, like what we defined before with our grammar. If we give it the string 1, 2, 3, we expect that it parses 123. That's as much of the string as it can. And then it returns everything that it didn't parse. In this case, it parsed everything, so it just returns us the empty string to indicate end of file. If we give it 1, 2, 3, ABC, then it's not going to fail. It's just going to parse 1, 2, 3 and return ABC. Because, once again, as much of the string as it can. And we might want to run another parser on the rest of the string. so we can chain things together. What if I gave it ABC123? Well, it should error, because it doesn't start with an integer. So hopefully it gives us a helpful error message, but here we go. So we sort of have the basic structure of our parser functions. We can maybe try to put them together. So this is sort of what I've said the type signature kind of looks like. It's basically just exactly what we said. A parser is a function that takes a string and it returns either a parsed type and then another string, and that other string is the unconsumed input, or it returns an error. And this is going to differ depending on the languages that we choose. Particularly the error handling is going to differ. So, next slide. How are we doing for time? Oh, terribly. So, the first language that I decided to choose is JavaScript. And because we're doing this in JavaScript, this part of the talk is, of course, best viewed on Netscape Navigator. So, we're going to start here with what a parser function looks like in JavaScript. And there are a few different ways, because JavaScript is very loosely typed. You can kind of do anything, and it just accepts it. This is a problem that I ran into when I was writing this part of the talk, trust me. And so what I've done here is I've just put in a type, just in a comment. A function is going to take an input, and on success, we are going to return a JavaScript object instead of a tuple. JavaScript doesn't have tuples. It has, like, lists, and you could use that, but I decided that if I'm just going to use a map, because JavaScript lists are just maps as far as I'm aware, we might as well just give them names. So the value is whatever we parsed, the input is whatever we didn't parse, and that's what it's going to return on success. And if we error, we're going to use exception handling. This is maybe a bit sacrilegious, but it's going to make the code a lot nicer, and this sort of gives us some things that we might otherwise have in like functional programming languages, like with monadic parsing. Don't worry about that, but it just gives us the nice error handling that we might expect out of parser combinators, just using exceptions, which is kind of fun. So here's a parser. You don't really need to know what all of this code does. This is just our parseInt function from before, but just written out in manual code. This is like not very nice, because I'm not very good at JavaScript, but what it does is it does exactly what we had with the little magenta blob earlier. It does this. But as you can see, it returns, a value and an input, and if it doesn't get a valid integer, it just throws an error. And we can do the same thing for other sort of simple parsers. So for example here, open bracket, it just tests if the input starts with an open bracket. If it doesn't, it errors. If it does, it just chops off the open bracket from the beginning of the string. This is not very exciting, but it is going to be useful, because then we're going to be able to combine these later on. For simple functions like this, a manual parsing approach is totally fine, and is, it's good, it's efficient, and all of that. So here's maybe some examples of how it might work. We've got the integer, chopping off the integer, giving us the rest of the string. Open bracket just doesn't return anything, but it gives us the rest of the input. Close bracket, same thing. Now that we have these simple parsers, let's put them together and make something more complicated. So, here's one. How would we write a grammar that parses multiple of our small symbols in sequence? And the answer is we just run them one after another. Now, just note, this is a little bit of syntactic sugar. Input, comma, value equals open bracket input. This is destructuring. JavaScript has destructuring. I didn't know this. I was blown away. It basically just means that we are parsing open bracket input and getting whatever it returns and just setting the input setting this variable called input equal to that, and the variable called value equal to the value. It's basically just we're parsing, and then we're just setting the input equal to whatever the parser didn't parse, and so through that we're able to just chain them together like this. So notice what I'm doing here is I first parse an open bracket, I then parse this inner list, which we'll define later. And I'm just saving the result because the inner list has the actual value that we want to return. And then I'm parsing a close bracket. And that is the function for defining a list. And it's similar to our grammar. It's basically an algorithmic translation of our grammar into the code with a little bit of extra stuff for, you know, like handling result types and things. Okay, what about alternatives? Well, since we used try-catch, well, since we used exception handling, we can just use a try-catch block. So, and if an element is a list or an integer, we try to parse it as a list. If that failed, we try to parse it as an integer. If that failed, then, well, it's a failure, so we just throw another error. And this is, you know, basically our alternative construction that we had in our grammar. What about a optional type? So if you remember in our grammar for our recursive list, which is what we're trying to parse right now, we had that the inner list could be empty. So how do we do something like that? Well, it's just another try-catch. We try to parse something. If it fails, then we just say, it doesn't matter, and then we just return an empty list in the input. And that's basically it. That's how you do optional types in this case. And then finally, we have repeated sequences. So this is a little bit more involved, but the idea with a repeated sequence is that we can have 0 or more of the same parser. So what we just want to do is we want to run the parser and just keep running it until it fails. And so this is just a while loop. Now, I've defined, this isn't what we're doing. I've just defined this sort of like helper function for comma then element, because if you remember in our grammar we had many commas and then elements, so I just defined a little helper function so that we could have some shorter code. And if I sort of try to, like, you know, if I just abstract that away, parsing a non-empty inner list is now going to be parsing an element, and then while true, we just try to parse a comma then an element. If it fails, we just break out of the loop because, you know, that we parse as many elements as we can. Otherwise, we just keep going. And in this case, I'm accumulating our values into a list, and then I'm just returning it at the end. Okay, so that was a lot of writing to translate our grammar into code, but it was in an algorithmic way. And so we've basically taken this parser, we've taken this grammar and just kind of turned it into a parser in a kind of like, yeah, this seems like it'll work. Does it work? Yes. Yes, it absolutely works. If we give it an example, if we give it some kind of recursive list, it just does it. This is a JavaScript list. This is not the string that we gave it. This is just a JavaScript list. And so, like, yeah, it worked. We didn't have to do any of that complicated stuff with matching brackets. We didn't need a stack because the stack is the function stack. Yay, right? It just works. And this is like the power of recursion, right? Because like we've just defined that like a list, like an element can be a list, and like a list contains a bunch of elements in a kind of like, this is how it's defined way, and it works. Does it fail when it's supposed to? So here's some unmatched brackets. Yes, and it gives us a helpful error message that it expected close bracket, which I think is really cool until you realize that if we give it another error, it also says it expected a close bracket, because this isn't as smart as you might expect it to be. Why didn't the error message change? Well, let's sort of think through it. Imagine that you were a parser. So you've been given this list, and you want to parse like in a recursive list, so you go, okay, it starts with an open bracket, and so I'm going to parse an open bracket. And then you say, okay, now it contains an inner list that could be empty, and what it returns to you is, oh, we failed to parse a list, so it's empty. And you go, oh, okay, so if it's the empty list, then this open bracket should be followed by a closed bracket. And that's why it's giving us this like error type. This is a bit hard to get around. There are other ways of doing recursive descent, which I believe are generally better with error values. And I mean, errors are a bit of a rabbit hole that we can sort of fall down, but the way that we're doing it is a bit unsophisticated, so this is just kind of working for us. And so we now have a way of turning grammars into parsers, just algorithmically. And you can now do this. You can now go home, write a grammar, write a parser, and run it, and it'll probably be fine if you did everything right. But like, it's not great, right? Like, we had to write so much code just to get here. I mean, every single one of those functions was huge. But like, as it turns out, oops, as it turns out, like, we can have our cake and eat it too. Wasn't this talk supposed to be about parser combinators? Well, yes. So parser combinators are sort of building on top of this recursive descent foundation that we've had, that we've created. The parser functions are going to look the same, but whereas a parser is a function that turns strings into stuff, a parser combinator is a function that turns parsers into another parser. Now, here's an example, just because that can be a little bit weird. Higher order functions are strange. Here's a parser letter. It just takes the first letter, from A to Z, and it chops it off the beginning and it returns it as a character. So our first combinator that we're going to be interacting with is one that I've just called 0 or more. And that's a function that takes in a parser and turns it into this new parser called 0 or more letters, or 0 or more letter. And what this will do is it's another parser that takes in our string and instead parses 0 or more letters, right? So what this is going to do is it's basically going to run a parser until it fails and return a list containing all of the values that it returned. It's a little bit strange to be calling functions like this as a function, but once you sort of get used to it, it's really not so bad. And like 0 or more letter, like that's pretty descriptive. Like that's what this parser parses, 0 or more letters, right? So that's good. So here's my implementation of it. There's a little bit here. So you notice that this is a closure here. This is how you define anonymous functions in JavaScript, also known as lambdas if you've used Python. So, well, maybe they're different. I'm sure someone is going to yell at me or whatever, but I feel pretty good about it. Basically, we are returning a new function, and this new function will take in input, and it will do what we basically did earlier. It creates a results value, which is just an empty list, and then it tries to parse the input as many times as it can, pushing the value to our result. As soon as we catch it, we break, and then we just return. So this takes in a parser, returns a new function, which is in and of itself a parser function. And you would use it like this. So, oh, this is a different, oh, hold on, no, this is a different combinator. Forget I said anything. Here's a different combinator. So this is this is a different one. I've called it seek for sequence. And so sequence is going to take in any number of parsers, and it's just going to run them all in a row. So this is basically the same thing as in our grammar when we had multiple symbols placed next to each other. So let's say we had two parser functions. One of them is called letter, one of them is called integer. Sequence of letter and integer is a parser that will parse a letter, and then it will parse an integer. So you can see that here I run seek letter integer, and I give it now A12, and what it will give me is a list containing A, and then the integer 12, and it'll say that it parsed all of its input. If I give it something that is not a letter followed by an integer, then it will fail, right? So this is just another parser, right? Yeah, a grammar like letter integer can be parsed by sequence letter integer. So this is my implementation, and it's just a for loop. It's, once again, I'm returning a function, and this syntax here, allows for variable number of arguments to the function. It just means that we can write sequence of letter, comma, integer instead of having to wrap them in a list. But parsers is just a list. So, yeah. But notice here that for all of my parsers, every parser in parsers, I just try to parse it. If it fails, because of exception handling, we will automatically just break out of the loop and return a failure state, so we don't even need to care about exceptions. This is why exceptions are actually really good for this, in my opinion. And then we push the value into our list, and then we just, yeah, it's what you might expect. Now, here's another one, either. This is kind of the mirror image of sequence. Instead of parsing a bunch of combinators in a row, we're parsing a bunch of combinators and just returning the first one that succeeds. So either letter or integer will either parse a letter or an integer, and if it can't parse either, then it will return an error. So this is our alternative in our grammar. And so here I've got either, and it's just for every parser in here, I try to return the results, and if it doesn't work, we throw an error. That's exactly what you might expect. Here's one that's a bit more complicated. This is not within the restriction of our grammar syntax. This is just something like entirely different. Could you write a combinator that like takes in a parser, like two parsers, one for elements and one for like separators, and then parses a separated list of elements? Yeah, absolutely. Combinators can be anything you want, really. I mean, this is pretty cool. So I've made separated list, takes in an integer, and it takes in two parsers, one for an element and one for a separator. Here I've given it integer and comma, and so now if I just give it a comma separated list, it will return a comma separated list. It will first, return the element, try to parse the element, and the separator, then the element, then the separator, then the element. It's a bit more complicated, this implementation, but it's basically just the same grammar as we had for our like recursive lists. If you remember, we had element and then any number of commas followed by elements. I didn't do this very well. Once again, I suck at JavaScript. Don't worry about my code, but like the point is what it's doing. It's taking in our parser and then our separator, and then it's just parsing them in sequence. And actually what I've done here is I've used parser combinators to make another combinator. So this is just our grammar. It is a parser followed by 0 or more separators followed by parsers. That's what our grammar was back in the beginning. And then all of this is just trying to get all of the values to be what we would expect. So we've done this has been a bit of a hike from 0 to parser combinators in JavaScript. But we now have a bunch of these combinators. Let's rewrite our parser that was like 100 lines long for recursive lists. Let's write it from the ground up. So VS Code time. Here we go. I have a little document here. I have a website which will give us our output. So I just need to put my input in here. So I'll just say 1, 2, 3, 4, and then, I don't know, the empty list, something like that. We don't have a parser yet, so it's not doing anything. So let's write it. Okay, so if we recall, our grammar was like item is equal to element or list, and element is equal to integer or list. I'm so nervous. And then we also had something like, list is equal to, in this case, we're going to have our separated list thingy. So that's fine. So let's just start with that. So I've already defined integer here in my parsers function. This is just the same integer function we had in recursive descent. So I'll just write that let element equal either integer or list. There we go. But we haven't defined list yet. In order to define them out of order, we're going to have to define it as just like a function. This is a limitation of JavaScript, but it's kind of hard to get around. So let's write a parser function. But, obviously this is just going to be, we can just use combinators in here. let's return separated list. Well, actually, hold on. It's going to be surrounded by square brackets. So before we do that, we're going to start by just saying, I've actually defined this other combinator here, which I didn't put in the talk, but you might want to have a look at it. It's called delimited. And this just parses something surrounded by brackets or whatever you want. So it takes in a delimiter, a parser, and then another delimiter. It tries to parse the first one, and then the second one, and the third one in sequence, and just returns whatever the second one did. So, like, for example, you could write a parser that's surrounded with brackets, but we throw away whatever the brackets function is returned, just for niceness. So it's delimited. The first parser is going to be, it just parses a string, which is just our open bracket. And then the second one is going to be a separated list containing elements as our elements. And then they're just delimited by another string, which is just a comma and a space. And then it's closed by a closed square bracket like that. So a list is a separated list of elements separated by commas, surrounded by brackets. And this is it. This is our grammar. We did it. This is our parser. It should work except, hold on, I have to run it on the input first, of course. Remember that, because this is a function, and so we have to do that. But there we go. And so if I run it, it should work. Save. Thank you so much. Save. There we go. We did it. We wrote a parser to parse. Thank you. Yeah, and it should handle errors for us. Let me just get rid of a close bracket. Error. Expected close bracket. Isn't this neat? Like, I mean, how many lines of code was this? Like 7? 1, 2, 3, 4, 5, I don't know. 7, something like that. Yeah, and so like, cool. And this just gives us that. And so you can see how, like, this is just a simple format. If you had more complicated formats, like for example, JSON, which can contain maps that contain lists that contain other maps that contain strings and also other things, like you can, like these sort of complicated formats, you just really need to write a grammar. The grammar for JSON is just on a single web page. You can Google it. It's not very long. And then you can just write it in a combinator, and there you go. So what did we learn from this? We learned that parser combinators are pretty cool. And they give us the power of recursive descent to parse complicated formats with the readability of a grammar, which I think is like just amazing. And they look like a description of the format. They don't look like some complicated function, so they're actually pretty easy to like understand what they're doing. And I learned that JavaScript is okay. I don't hate it. But now let's do a better language, which is called Rust. So I'm being inflammatory. I love Rust personally. It's a language that I've used so much. And it's taken a lot of cues from many different languages, including JavaScript in some places, as well as other languages like Haskell. Haskell is a functional programming language, and functional programming is where this whole concept came from. So, like, it actually does pretty good. And I changed the color theme for this section just because I think it would be cute. So, we defined combinators in JavaScript, but let's not do that again. I don't want to do that again. Normally, if you were going to write a parser using combinators, you would just use a library, because there are so many libraries that people have already defined. And the one that I like is called nom. This is the logo for nom. I think it's quite cute. So first things first, let me just go to the nom documentation. Let me bring it up here. Here we go. It's on GitHub. Eating data byte by byte. Nom was originally designed to parse byte sequences, but they found out that you can kind of just parse anything. In fact, as we'll see, the definition of a non-parser does not depend on strings or anything. The definition of a non-parser is like so generic. Let me go to what it looks like. So Rust has static typing, unlike JavaScript, which has no typing, which makes our parsers more robust at the expense of some ergonomics, because we're not going to be able to just return a list containing other lists. We'll have to do some more complicated stuff. We're not going to rewrite the recursive list. I don't know if I have time, but like, yeah, it's interesting. But we can still do some typing stuff here. So this is a lot to take in. But let's have a look at this. So Rust has something called an enum. And you might be familiar with this if you've ever used Haskell. It's basically a sum type. And this has so many different names. It's called like a data type, a sum type. It's called an enum here. It's called a tagged union. Anyway, we're calling it an enum because that's what Rust calls it. An enum sort of, and here's the explanation, an enum sort of represents that a type can be one of multiple alternatives. So in this case, we have this result type, which could be OK, containing a T, or error, containing an E. And so in this case, if a function returns a result with T and E, then what it's saying is that if the function succeeds, it will return OK with a value of type T. So in this case, this returns a result string standard IO error. If read to string succeeds, it will return OK with a string inside it. Notice here, OK string, and then we can print out whatever the string is. If it fails, it will return error with a standard IO error inside it. So it's like a type can be one of multiple alternatives. Let me go back to here so we can have a look at this again, because there's more enums. We also have this one, which non defines, which is all of the different ways that a parser could fail. There's actually 3 of them here. The first one is incomplete, because non was designed not only just to be able to handle string formats and other things, but also things like binary formats that are streaming and aren't complete. So you might still be waiting for data, but you can still start parsing your data, because, I mean, you know, maybe your web framework sending out TCP, I'm not a web developer, HTTP requests and receiving your data in packets, but you want to be able to do some work on it. So we can return incomplete, but we're not going to be doing that. We could also have an error, and this just means a recoverable error, just like all of the stuff that we've been doing. But we can also have a failure, which is when you know that your error is so bad that you will not be able to parse anything, you can just return failure, in which case it will do no more work and just instantly jump out and return an error. It's just for performance reasons, basically. And so now our parser function returns a result, because it can fail. If it succeeds, it returns a tuple containing our input type, which comes first in non, confusingly, and our output type. This input type can be anything. String, vector of tokens, if you're parsing a programming language. It could be a vector of like a bunch of bytes. It could be literally anything. It's just a generic type. And then it returns O, which is just some kind of output type. And if it errors, it returns an error with E. And this is where we can define our own error type. So, for example, get out of here, Osaka. Here is the type of our non-negative integer parser from earlier. So we're returning, oh, this should be U32 because non-negative, unsigned 32-bit integer. It doesn't matter. We return, in this case, by the way, I result. Let me just, I forgot to write this into the talk, but if we go to the documentation for non here, what they've done is they've defined a sort of nice, simple way of writing out this result, this sort of error type, and it's called iResult, which contains iResult, our input type, our output type, and our error. And the definition of iResult is it's just a, it's just a type def. Where is it? Type def. It is exactly what I just wrote on the board. It is I, comma, O, and error. So it's just the same thing, but we've just given it a sort of easier to write name. And this E is sort of predefined, so we don't even need to write the E. Like it can be, by default, it just returns whatever like nom's default error type is, which is confusingly also called error. I hate that, but it doesn't matter. So going back to the talk, we have this iResult, which is the input type is strings. This is a string slice, so it's a reference to a string in memory. This is where we get to some of Rust's like performance things. You can write really memory performant like code because it's very complicated, but for that complication you get a lot of performance. In this case, we don't have to do any copying. And this is going to be really beneficial for when we, for example, return our unconsumed input. We don't have to copy from the string and return a new string. We can just reference the string at a certain position. And here, we return an integer, 32-bit integer, which Rust calls an I32, or an integer parse error, which we could define on our own. But if we didn't want to define our own error type, we could just leave it out, and then it will just use whatever nom deems its default. Okay, so what I wanted to do is to write a small parser, but we don't have time for that. So unfortunately, all I can say is if you want to learn about nom, then there is a lot to learn, and I'm just going to have a look at some of the documentation, but it's so fun to use. I love this. I once wrote a JSON parser in an afternoon for fun. And JSON is not a fun, it's not funny. It's not something where you would just be like, haha, I wonder whether I can do this. It's boring. And yet I did it because I just wanted to. And this is just the insane thing about parsers, that they turn you into a madman who just can't stop writing parsers for formats that already exist. So anyway, going back to some of the nom documentation, because nom is just a library that contains a bunch of helper functions that you can use, it's got a nice little list of all of the different combinators that you might want to use. So let's go over a little bit of a highlight reel. We have some pretty nice ones. For example, I like some of the, it doesn't have it here. Oh, here's one. Tag, this is our string function where you can it just parses a string. You can have one of, and then any number of characters, none of these characters, so it'll parse anything that's not in the pattern. All of these different stuff. These are mainly just for bytes. You also have some more other combinators. So for example, alt, this is our either, alternative, and it just takes in a tuple. We'll have a look a little bit more at that in a moment. Permutation is interesting. That's pretty cool. Succeeds when all its child parsers have succeeded whatever the order. So anything that you could think of is just someone's written a parser for it. So cool. We also have our nice sequence combinators like delimited, and here we also have preceded and terminated, which parses something before a parser and after a parser respectively. We have other things like separated pair, which is a tuple, and we also have other things like they have separated list. So here's separated list 0. They also have many 0, this is 0 or more. A lot of them end with 0 or 1 as sort of indicating whether they can parse 0 or more or 1 or more, stuff like that. And just looking through these, there are so many. There's even some very functional programming-esque combinators, such as fold many, applies the parser 0 or more times and folds the list of return values. So you give it a function that is an accumulator function that scans over the list and accumulates all the values into something. So like, that might be a little hard to explain, and I don't really have enough knowledge of how it works to give you a demo, but like the idea is that you could have a one-liner that parses a sum and sums up all of the contents and then just returns its sum. And that would just be fold many 0 and then just like a separated list where the values are integers and the separators are pluses. And then you would put in a fold function which just sums all of the results together. I'm assuming that's what it is. But like, and this is what they've done. They've done it here. So this is just an addition function. And then we have like many, I don't know, in this case they're just using bytes. But like, yeah, I don't know, it's pretty cool. And they've got many parsers. And once again, not really enough time to write one ourselves, but we can have a look at maybe a parser that I wrote. Here's one for a programming language, which we're going to talk about a little bit later as sort of an honorary mention. So a programming language tends to have 2 parsers. I wrote this once again in an afternoon, so it's not very good looking, but you'll just have to stick with me here. So here's an example, right? The first thing that this parser is going to do is it's going to take the text of the program and it's going to split it up into all of the symbols that make it up, which are called tokens. And so these are all of the different tokens. My programming language looks a bit like this. It's just sort of no semicolons on the end, you know, let identifier equal number, and so on and so forth. And so what this does is, like, we can see that here we have something like, we have our alternatives. So a token is either an integer, a boolean, a keyword, or an identifier, which sort of have the same structure, but so that's why they're sort of stuck together in a function. Or punctuation, which I've sort of grouped together to mean like comma, semicolon, new line, stuff like that. And so it reads very similar to how we wrote our other parser combinator. And we've just got a bunch of other just like things here. Here we have our integer again. Check it out. We've got 1, 9 equals characters from 1 to 9. And so now we've got our parser is going to be either 0 or a tuple containing 1, 9 and any number of digits. This is our integer parser that we had earlier. It just looks a little bit different. Arguably worse. But that's just because NOM is really complicated and you can do a lot of stuff. So, like, we can do this. Let me just demo it. I've got my thing here. AST, no. /AST. Hey, it worked. And also you'll notice that there weren't very many dependencies. It compiled very quickly because NOM, once again, it's just a library that contains a bunch of functions. You don't have to pull in any kind of complicated library or anything. You can just, it's just a bunch of functions. I mean, there are a couple of libraries it depends on, but not very many. And I'm not going to bore you with this toy language, but like it works. And it's super quick. No copying or really anything. And so, like, yeah, if you want to just write a combinator, you can just pull in an external library like this, and it will work. But there are a couple of idiosyncrasies when it comes to Rust. For example, one thing that I should mention, remember how I said that JavaScript doesn't have typing, but Rust is like strictly typed? Well, the alt combinator has a bit of a restriction, which is that, and don't try to read these type signatures. This is like arcane Rust. Like this is not entry-level Rust. But the whole idea is basically, if you've got an alternating parser, like you can't return either an integer or a string. You have to know what type it's going to be. They have to return the same type every single time. And so for that, you might define an enum, right? But that means you're going to have to define a bunch of enums. And so you do have to do a little bit more work to get a non-parser to work. But at the end of the day, like, you also get the robustness that you get from static typing, so it's a bit of a trade-off. This is like this is cool. I'm a big fan of nom, and I've used it a lot. You can go and check out the stuff that I've done on GitHub after I make it public, because I forgot to do that. Okay, so another thing, and this Rust part, this is the last part of the Rust part. But another thing that I thought was really cool, just to sort of show off, it's just a fun little Rust thing, is the parser trait. So I showed you the definition of those functions, right? They have a certain type signature, but it doesn't have to be a function. In nom, a parser is anything that implements the parser trait, which has a function defined on it that parses functions. Sorry, that is a parser function. And that's a bit strange. It's like a Java interface, if you've ever used something like that. It just defines a bunch of functions that a type can implement. But you can implement a trait in Rust for like any type. There's some restrictions there, but like, for example, let me just show you the parser trait. So non-parser is a trait, and it contains this parser function. And this is what you would expect. It takes an input I, returns I result, an input, output type, error. Right? This and mute self is just because it also has a reference to itself, because it's like an interface. You have to be able to reference self. God, that was the worst explanation of traits that I've ever given in my life, but I don't have time. And so, like, this is pretty cool. These functions are all given for you, so you don't have to implement these. You just have to implement the parse function, and it'll give you a bunch of stuff for free. But what's interesting is you could implement the parse function. You could implement the parser trait on, I don't know, a string. You could do that. You could implement the parser trait on a string. We could try and do that now. I haven't tried to do it, so it might be a little bit perilous. But the idea is just that then, if you implemented the parser trait on a string, what you would be able to do is you would be able to write code like comma dot parse string, like that. And then it would be a parser, and it would return whatever you want. And a real-world example of how they've done this in nom is that tuples of parsers are parsers. So you can write, for example, letter integer dot parse a12, and it will return exactly what you would expect. It would return a letter followed by an integer. I've sort of put this on the slides a little bit. I just think this is so cool. Look at that. Like, this is what you would expect to happen. You can also then parse them into, you can pass them into combinators. So we could have many zero tuples containing a letter and an integer. And because it works with the parser trait, it will just work. So I think that's kind of crazy. And this is, like, it's not dynamic typing. It's just that the compiler will go and look at all of the different ways that you've used these parsers and generate a separate parse this tuple function. And so it'll generate all of these monomorphized types, which will basically, at the end of the day, it just means that we can write this kind of, like, quote-unquote dynamic typing, but we don't have to pay for it. We just generate a bunch of differently typed functions that parse different types of things. And once Rust is complicated, I don't have the time to talk about it, but it's really cool. I just think that's amazing. It's one of the coolest things I've seen about Rust. So, no, we are not going to write a parser in Rust. What have we learned? Rust is pretty cool. This is an artist's impression of me watching you all learn Rust after I showed you this. We get the benefits of combinators with blazingly fast performance, and the type system gives us a degree of robustness that we didn't get in JavaScript, because we know that if a function says it will return an integer, then it will return an integer, or if it says it returns a result integer and an error type, we know the integer that it returns, and we know how it can fail. So it gives us some great robustness. And this is awesome for parsers, because parsers oftentimes have strictly defined requirements on them. But it does mean we have to work within static typing. So we now have to define a million enums just to get the things that we want. So it's been a journey, and we have one more programming language to look at, but it's more of a funny addendum than anything else. So I've decided to put the conclusion before I talk about C, just so that we're not that bored or kind of worn out when we talk about these things. If I had my way, this talk would be 5 hours long. This is what I've subtitled this section because, oh my god, there's so much to talk about with parsing. I go insane. So first things first, we didn't talk about functional programming, but that's okay because, you know, this is a style. Like functional programming, we've done functional style programming today, but none of the languages we looked at today are functional programming languages. In the case of JavaScript, it's not even functional. We didn't even talk about the fact that parsers are a monad, but I don't care. And look, if you want to learn about functional programming, like I tutored Comp3400, I love functional programming. I think it's super neat, but it's so much. It's so much stuff to talk about. Comp3400, you should take it if you think it sounds interesting. But just the Cliff Notes version is that functional programming is a way of styling, is a style of programming, or a kind of programming language that, like, it's very hard to define, but it tends to be like, the common theme is that it is built around pure functions, which are just functions that take in values and turn those values into some other value without doing any kind of side effects like mutating global state or mutating functions in general. There are no mutable functions in Haskell, or even things like printing. That's side effects, so you have to get around that using some complicated things. If you want to understand why and learn how to write code like this insane, arcane incantation, then Comp3400 is great. Programming languages? You could write a programming language with this, but it will take a little bit more work than just what we've sort of talked about. Programming languages are very cool, but they're not just parsed into the sort of data types that we've been talking about. Instead, they're more complicated. They have like 2 stages, usually, or at least 2 stages. One of them takes our string. You have one parser which takes the string and turns it into a bunch of like symbols that build up the programming language. And you have another parser that analyzes those symbols and turns that into an abstract representation of the program. So it's very cool, and it's a really interesting thing, I think, to sort of fall down the rabbit hole in looking at. So like this is an example of what I mean by the symbols. So we have like this simple Rust program here, or JavaScript program. It doesn't act, oh wait, couldn't be JavaScript. There's no brackets around the condition. And so what this is made up of is just like, you look at the symbols, you don't care about things like white space. We instead just parse it into what's important. So if, we have an if keyword, and then we have an identifier I, and then we have an equality operator, EQ. We have an integer 1. We have a curly bracket, and so on and so forth. And this is what the Alexa does, and then you run the parser on that. And if this interests you, Comp4403, Compilers and Interpreters, is like the better version of this talk. Actually, it goes way more in depth and talks about programming languages and static checking and code generation and interpreting and all of that sort of stuff. It's so much more. So you should take that. There are other methods of parsing. You don't just have to use combinators. For example, what if you don't want to write a parser? Parser generators. You can just give a program a grammar, and it will spit out a program to parse that grammar. So there are some sort of trade-offs for this. Obviously, you're now going to have to deal with generated code, which is not nice. And you're going to have to, for example, bring in a dependency, a whole other program to build your program. But it's certainly very quick, particularly for complicated formats. It's really good. If your data format is simple, you can use something like regex. Regex is fine. I quite like regex, but what I found, this is very surprising to me. When I was writing my parser for my video game, a simulator of an arcade rhythm game, and I had to sort of parse the the format for defining like the songs and the notes and stuff like that. And it was basically line by line, so I figured I could just parse every line using regex, or I could parse every line using parser combinators. I'll just test it out and the benchmark. Regex was slower, and that surprised me. Regex was slower, ignoring compile time even, like just to run the regex. It was insane. But regex is definitely going to be faster if you just want to test if, for example, a string matches a format. Because, yeah?
Sorry, why compile time? Do you mean the time to compile the program? Or the time
Oh, the regex. So the regex crate in Rust has to compile the regex first. And so, for example, if you're running a regex in a loop, if you're compiling it every version of the loop, that's like an anti-pattern, and it will ruin your performance and stuff like that. But even without that, I found it was slower, and this isn't going to be the same for every use case or every computer, so it's not like regex is slower than combinators, it's just that in this particular situation, it wasn't. So, but if you're testing if a string matches a format, regex is obviously going to be so much faster because that's what it's kind of built around doing. Language doesn't support combinators, you can use recursive descent, there are other methods, just use a parser generator if you want, stuff like that. When I say language doesn't support combinators, what I mean is that, remember how we were returning a function from a function? There are a lot of languages that just don't have that. C is one of them. Comp 4403 covers some other methods of parsing. Recursive descent is not the only one. And actually the recursive descent that we've done is backtracking recursive descent. You also have, for example, symbol look ahead and other kind of things that just no time. I've said no time so many times. So before we look at C, not in depth, just to sort of laugh at the terrible implementation of combinators that I did. Here's my conclusion. Parsers are really fun to write when you know what you're doing. And I didn't know what I was doing when I started parsing, and I hated it. But when you have a little bit of a thought about how your format looks, and you sort of turn that format into something, it's just a joy. I can't really say it in any other way. I just love parsing. And combinators are a nice solution if you just want to write code, like you don't want to deal with externally generated stuff, you don't want to deal with an extra library or whatever. You can just write functions and they give you parsers, and it's nice. And there's a high degree of flexibility and readability. And in the case of the Rust project that we looked at, it is so performant. It is more performant than the C version that I wrote, because the C version I wrote has to do a bunch of dynamic allocation that Rust wouldn't have done, because with Rust it monomorphizes all of your functions, which like it's just different ways of doing polymorphism, and I don't know, it's very performant. I found it to be super fast, and I love that. Here are some exercises. If you thought this was cool and you want to go home and write a parser, I have a couple of suggestions. Invent your own configuration language, like ini or JSON or whatever, and parse it. I think that's pretty fun because you get to invent your own grammar. If you like maths, write a parser that analyzes logical expressions. You probably want to look up how to write a grammar to parse like expressions, like arithmetic logical expressions. There's a lot of pitfalls when writing that to do with things like infinite loops, infinite recursion, and prints out its truth table. This was a UQCS code jam question this year, and I tried to do it using parsers, and I was so rusty, and and I couldn't get it done. And then I went home and I did it that night. So it was like, it was fun. Write your own dialect of the Lisp programming language, because if you want to write a programming language, Lisp is like easy. It's like the syntax is like nothing. SICP approved, structured interpretation of computer programs. That's a textbook about Lisp, and it goes over writing. I think it goes over like basically writing an interpreter for Lisp. I don't really know. I haven't finished it. Here's a great one. There's $1 million prize if you can write this. Okay. In conclusion, before we talk about C, thank you for coming to my talk. I really appreciate it. Now, I'm gonna say C like this is more like laughing at how stupid this idea was. So my C idea, how do you define a parser in C? So first things first, C, once again, you can't create functions at runtime, right? You can in GCC, but not generally. So what I decided on was this struct right here. So you have to have, like, how do we, like, if we've got like think about like how a closure works, right? We've got like a function body which we've written at runtime, and it takes in some elements of its like, of its environment. So it takes in, like, for example, in our parser functions when we had like many 0 or something like that. There we go. So we had like, you know, like delimited. It takes in like 3 parsers, and it sort of like stores them somewhere, and then when you call the closure, it uses that data that it's stored somewhere, and it runs it through the function body. So instead of that, what I decided to do, I closed my C file. So the data that is stored somewhere is just going to be void star. Void star is how you do polymorphism in C, or well, it's one of the ways you can do it. It's a bad way of doing it. It sucks. Void star is a pointer with no type, and so it just points somewhere. And then we have this parse function, which it takes in a string input, it takes in void star data, which is our data here, and it takes in an address to write the result. And I'm just, once again, we've got a while true loop, we're parsing the input data, we're pushing the result to the vector, and then at the end we return the output. So this looks a lot like what we've done earlier, because I haven't shown you the implementation of the vector. This is a mem copy. Vec push, first, it does maybe what you might expect, but here we have to cast the data, of the void, of the vector to char star, and then add the size, the offset into the vector, and then write memory to it. Like, this is so bad. because it's like just memory manipulation, raw memory manipulation. But the question is, does it work? It works. Well, it should work. So what I've done is I've made a parser, and it's 2 parsers in sequence. Many copies of the tag it, so tag, once again, that's just a string. Many copies of it, followed by a single character. So if we give it it works, we should expect a vector containing 5 copies of the string it, and then a single character containing W. If this succeeds, it will be a big W. Make it works. Anyway, so this is what I've been working on for the past few months. And, well, actually this I wrote in, started writing it at 8 a.m. in an operating systems architecture lecture. But yeah, I had a lot of fun writing this, and I really hope that you can go home and just try it out, give it a go, see if you like it, and or at least just have this kind of tool under your belt, because writing parsers is so common. It's just it's like a sort of bread and butter thing for programmers to do. Though to be fair, oftentimes we do just sort of give up and use JSON and just try and fit JSON into what we want to do. I don't vibe with that, but I understand it. And yeah, so honestly, this is it. This is the end. Thank you so much for coming to my talk. I appreciate it.
Thank you very much, Luna. Hopefully you've inspired us to write parsers in Rust and not C. So as a token of our appreciation, a UQCS mug. Thank you very much again. If anyone in the room or anyone watching on YouTube or the live stream would also like to do a talk and also get your own custom UQCS mug, look out for an announcement soon. We will be taking expressions of interest for talks next year. Don't forget, this Thursday we also have our movie night with SAS, so look out in UQCS Discord announcements for that as well. Apart from that, thank you very much, and pizza is outside.